Now we have our next speaker, Felix Cremer. He received his diploma in mathematics from the University of Leipzig in 2014. In 2016, he started his PhD study on time series analysis of hypertemporal Sentinel-1 radar data. He is interested in the use of irregular time series tools on synthetic aperture radar data to derive more robust information from these datasets. He worked on the development of deforestation mapping algorithms and on flood mapping in the Amazon using Sentinel-1 data. He currently works at the Max Planck Institute for Biogeochemistry on the development of Julia data cubes ecosystem in the scope of the NFDI4 Earth project. The Julia Data Cubes organization provides easy to use interfaces for the use of multidimensional radar data, raster data. So I would like to welcome Felix Cremer.
Yes, so I'm now going to talk about the on interactively plotting and analyzing large data sets. As we saw in Simon's talk, especially with the new generations, we will have a lot of data that is very large, and we need to handle this some way. And I think Simon, did you use pyramid schema already in your example? Not yet, but I mean it's on the edge of what is possible with just plotting your data. And the data sets we use, I mean the MetaOp data or the geostationary data that Simon showed is 11,000 by 11,000 pixels, and this is rough. It can fit into your RAM, but it won't fit on your screen because your screen will downsample this anyway. And so we can also downsample the data beforehand and then use this downsample data for analyzing and also plotting. So the idea I want to talk about today is so-called pyramids. So what is a pyramid? It's also called overviews in GeoTIFF, for example. So the idea is that we have some high resolution data set, and then we can basically build a pyramid by aggregating the data together. So we go from high resolution to lower resolution to even lower resolution, and by that we, as highlighted here, we basically decrease the size of the data, which then can be used to actually plot it. Because and then we only need to load or even download the data that we are currently looking at, and not the whole data set underneath that might be very large. And so as you see here, we go from very fine scale structure to very coarse structures. And so we developed this package called Pyramid Scheme to then both prepare these data sets to basically downsample your data from high resolution to coarse resolution, but then to also work with the data to plot it, to analyze it. So for computing these pyramids, there's basically two ways. So either you can start with data that is still small enough to fit into your screen. So this is 30 arc-second resolution, so it's a few thousand by a few thousand pixels. So you can just resample that on the fly. Takes you about a minute, and then you're ready to go. And then you can just plot it interactively. Or if you have higher resolution data, like 100 meter, 10 meter resolution, you'd like to do this on the disk. So you start with in this example, a ZAR data set, and then you can just build your pyramids on that. You can always choose your resampling function, and also the size of the permit or the size of the coarsest resolution layer. And then this will take some time, especially for very large data sets that might take an hour or a day or so, but that's basically a cost that you pay once. And then you can access the data. So you can currently in Permit Scheme, you can access ZAR data that is following this a certain currently emerging standard of how to save these overviews into a ZAR file, or GeoTIFF data, and these are either locally or in the cloud. So you can have your permit data somewhere on the cloud, and then you can access it from whichever computer you currently have. And then you can just use Maki to plot this. I'll show an interactive visualization later. But basically that is then what you have. You have your permit object, you just plot it, you say you want a color map, you want this color scale, and then you just get a normal Maki plot. This is currently working mostly with GLMaki. In WebGLMaki, this is still a bit slow, and I'd like to spend the week to also explore whether we could make this a bit better. And then, because these are basically just arrays with other arrays, we can also do lazy computations on them. So the idea is that we have this permit, and then we have another permit, and then we can just do combinations of this. So here we have the biomass data for 2020 and for 2017, and we want to know where in the world did we have growth in biomass. And so you can do this dot minus, and then you can, and this is basically just pre-registering the computation. And then as soon as you start plotting, this will just do the computation on the fly on the area that you're currently looking at. Because if you would do this on 100-meter resolution, this will take 2 hours or so. But if you do it like this, you would get a plot of your coarse resolution immediately, and then you can zoom into the areas that you're interested in or that on a high level look interesting because there's something going on. Yeah, and then and now basically what we are currently working on and what is in the making is like what Anshul also showed yesterday was spherical spatial trees of lazy reprojected data. We can combine this with permits, so we can have a data set in one projection. We can have another data set in another projection, lazily reproject them on the fly onto the same grid and projection, and then do computations on them. Or in this example, I'm going to show the AGB data that is in lat long, and then we project this on WebMercator so that we can also plot it on Tyler. So I already pre-plotted this. So this is a Tyler map underneath, and then we have a permit plot on top of it. And now we can just basically we can zoom wherever we want. This is a bit slow because this is currently pulling both OSM tiles and the data from somewhere on the web on this Wi-Fi connection, which is not that fast. So I think at home that would be a bit faster. So and there might also be some improvements we could be doing beforehand. But then you can basically zoom into the high resolution, and then this is an example of the Amazon fishbone patterns of deforestations. And no, that was not where I wanted to click. So Yes, as an output, what we are also looking into is pyramids on multiple dimensions, because you might not have the highest resolution in space, but you might have a very high resolution in time. For example, these older generation geostationary data sets, you have still handleable amount of data in space, but then you have it on every 15 minutes, and that for decades. And then basically you won't be able to fit all the data into your plot or into your memory if you would do it for every time step. And so we want to explore how we could do pyramids in multiple dimensions, either making a pyramid for every time step or even thinking about making pyramids in time of aggregating a long time and extracting the most important features. I'd also wanted to explore other formats that might have overviews, and also integrate Discover Engine for doing more computations. We're currently also working on making this combine nicely with observables, so that you could have sliders in Maki that have some input into your computation, and then this could be done also lazily, and by that opening it up for more use cases. Yeah, and that's it.
Very nice. I guess my question is, so imagine that you have a kind of a large NetCDF data set, right? That's hosted somewhere online. It won't contain the overviews.
Yes.
Right? So you need to generate them and save them somewhere. My question is, in that use case, do you need to resave the highest resolution, or can you dispense of it?
I think we could make a way to not have to resave the highest resolution. I think because, I mean, one use case. I think one use case before that is having data that is in overviews, and basically you have a lot of these data sets where you have tiles of geotiffs, but your data is globally, but it comes in 1 by 1 degree tiles. And then what we want to explore at some point is basically, if all of these have overviews, we could stitch together the overviews and then save the coarses levels of your pyramid somewhere else. And I think also for the NetCDF case, you could basically say we can stitch together all of the NetCDF so that they look like a disk array, like one single disk array. And then basically there's some indexing knowledge somewhere that we know, okay, if you're in this area, this is this NetCDF file. Basically like Kerchunk a bit. Okay. And then we could have a way to know, okay, the pyramid levels are over there. This is currently basically the structure of the pyramid itself as a struct is you have a base level that is a dimensional array, and you have a list of sub-levels that are also dimensional arrays itself. So you can very easily replace whichever level by, it's a convenience that you have in ZAR that you follow this format, and then you can just say pyramid of ZAR file. But you can very easily say, okay, pyramid of highest resolution and all the other levels, which will just be a list of data sets.
Okay, great, thanks.
So what kind of storage overhead does that imply, building the pyramids?
So the theoretical limit is basically 1/3, because you add 1/4 of your data for every So a power of 1/4 for every step of your pyramid, which basically is then at most 1/3 of your data in the spatial case. If you would have the temporal case, if you would only do one dimension, it's I think 1/2 of the data. But yes, that's something to discuss or to think about in the future of how to do these combinations of multiple dimensional pyramids.
I guess I was going to ask about nonlinear combinations of data sets, right? So if you have two high-resolution maps and you want to do, say, the cosine of one times the sine of the other, then the pyramid needs to be rebuilt as soon as you define the combination, right? You cannot do the combination of the pyramids. Is that kind of how do you look at that?
I mean,
if you want to derive, you have two fields. I think you meant earlier you said that you want to add more computational options on manipulating the pyramids and combining them.
Yes.
If that combination is non-linear, right, you cannot do one pyramid and then just combine it. You need to do the non-linear operation first, and then the pyramid.
Yes, this is in nonlinear cases. This would be an approximation of. There's a difference between doing the function and then doing the pyramid versus doing the pyramid and then doing the function. But I mean, yes, that depends very much on the applications you do on top of your pyramids. But I think as a first approximation, you're in a lot of cases still good enough to at least first see something and then maybe wait for the proper computations. Or you could think about zooming into the highest level at certain areas and not that you might be interested in anyway, right? But yes, there's in nonlinear cases, it's not always the case that the computation on your pyramid is the same as doing the pyramid on your computations. That's a trade-off to make, yes.
Yeah, no, I guess, and so that's something that the community has not sort of designed a strategy around to make it as correct as possible in a sense.
Yes, but I think that's always dependent on specific use cases and whether that makes sense to do the computations on a pyramid.
No, totally. I mean, this is not a criticism, it's more of a curiosity question.